Lab 1 by Justin Siegel. For this lab, I rolled a standard 29.5-inch circumference basketball that has a diameter of 0.24 meters and a mass of 0.62 kilograms across the hall in an almost straight line, as can be seen in this video. After filming, I imported the video into Tracker and started by implementing the diameter of the ball, as can be seen by this blue line. I then implemented a coordinate plane with the positive x direction going to the right. If I were to flip the axes, as in the negative x direction is to the right, then the velocity will be the same, just negative, as we'll see later in my code. This will change position versus time graph as well as the velocity versus time graph. The ball travels in the positive x direction with no movement in the y or z directions, as can be seen by this video here. After this, I imported the starter code into GlowScript. There are multiple things I had to change, such as the mass of the ball to 0.62 kilograms, the initial position of the ball to 6.989 times 10 to the negative 2 meters, and the initial velocity to the average velocity, which I created using change in position over change in time. I then put the starting time and the delta t. Under my while loop, I had to change the Fnet to 0 as there were no forces acting on the ball during the time frame. There was an initial push force when I first made contact with the ball, but during the motion I tracked in Tracker, the ball was at a constant velocity with no forces such as friction acting upon it, as we were supposed to negate friction due to the small sample size. Then, using Newton's second law, I had to edit the velocity update formula so that it was velocity final equals velocity initial plus Fnet, which is 0, times delta t, as well as edit the position update formula so it was position final equals position initial plus average velocity times delta t. I then ran the code where GlowScript created a computational model for what the motion of the ball should look like, as well as a position versus time graph and velocity versus time graph. The position consistently increases as time increases because the velocity doesn't change, as seen in the second graph. I then created a second GlowScript program as if the x-axis was actually going in the negative direction. As can be seen by the computational model, it would be looking like it's going to the left, and the position versus time graph would have the exact same slope, yet in the negative direction, and the velocity versus time graph would look the exact same, yet with a negative velocity. Finally, I transferred the data from both Tracker and GlowScript to create a line graph that displays both the observed velocity and predicted velocity versus time. As you can see, the observed velocity line is neither straight nor constant, and that is due to the fact that friction was actually acting on the ball, which slowed it down as the ball traveled further. That is why the blue line, the observed velocity, is lower than the predicted velocity, the red line, and gets farther away as time goes on. The net force is 0, as in the y direction, the normal force and gravity cancel each other out, and in the x direction, the ball has reached constant velocity when the video and Tracker was taken, so there are no forces acting against it to slow it down or speed it up, as we are ignoring friction. Thank you so much for taking your time to view my lab.